Okay, continuing on with problem number 1, part G. 16 grams of the unknown compound is placed in a half a liter container at 200 degrees Celsius. What is the pressure? So that is a PV equals nRT problem. We're solving for pressure, so P equals nRT divided by V. So let's go ahead and put in what we know already. We don't know the moles, but we know that R is 0.0821, and we know that 473 is the temperature. That was taken by adding the absolute Kelvin value of 273 to 200, and we know that the volume is a half a liter. In terms of the moles, we got to convert the unknown compound, which was CH4O, so that is going to be 12 plus 4, that's 16, plus another 16, that's going to be 32. 32 grams per every 1 mole equals 16 grams per every x moles. We can do the math here, but we see that that's going to be a half a mole. So that's going to be 0.5 moles in that case. So then in my calculator, or this calculator that somebody actually left in my classroom, second motion on, clear. There it is. I'm going to go 0.5, and then I'm going to times it by 0.821. Then I'm going to times it by 473. And then it's going to equal that big number, and I'm going to divide that by 0.5. And I'm going to get 38.8333. There's two significant figures in this problem, so I'm going to go ahead and round it to 39 atmospheres. Now that's a lot of pressure. And this is a big molecule, which, and this was part 1, which allows us to move on to part 2 and reflect on this. What assumptions? Well, we're making the assumption that this molecule that's essentially at a very, 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 very high temperature wants to expand fully. So the assumption is that it's an ideal gas, that it's nonpolar and small. When we say small, we mean it's got a very low molar mass. But that is the assumption we made. The assumption we made is that it is an ideal gas. So let's go on to 3. Given the structure of the compound, and let's reflect back on that. You know, this should have been a red flag for you immediately, that this polar structure does not want to fully expand. It's going to stay together a little bit. Because of that, if these are the walls of the container, it's not going to expand to hit those walls of the container. So we hypothesized that the pressure would be lower. Okay, polar non-ideal gas does not expand given stronger intermolecular force interactions. Okay, we can go on now to problem number 2. Oopsies. This is so ridiculously ghetto. Why don't I just go get a stupid eraser? What's my problem? All right, whatever. Okay, there we are. All right, so we have problem X and Y. We're going to decode these again. What is X? So in the first problem, what is X? So X, if you start on the high side, is 1s2, 2s2, 2p6, 3s1. So X is sodium. And Y, starting on the high side. This problem's a little weird because the high side is the left side, and they also add this big branch between the 1, energy level 1 and 2, but they don't between 2 and 3, and we're like, whatever. But in this case, 1s2, 2s2, that C hump is a little weird for people. How do we know? Is it 3? Is it 4? Well, it's always going to be a whole number. If it were the same height, it would be 2. If it were obviously double, it would be 4, but it's not, it's 3. So we know that Y in this case is nitrogen. Provide the formula for the unknown compound. Well, look on the periodic table. Sodium wants to lose 1 to be like neon. Nitrogen needs to gain 3 to be like neon, and that's going to be Na3N. We could have done it the way we did when we first learned ionic compound Lewis structures, where we would draw the actual transfer, and in this case we'd have to bring in another 2 nitrogens to fill those spots. But we're left with this binary ionic compound. We're going to provide the name for this. Well, the first thing is not a transition metal, so we don't need to say sodium 1. We just say sodium. And that is not a polyatomic ion. Polyatomic ion would look something like nitrate, but it's not nitrate, so it's nitride. I did a table. Okay. And now we're going to go on to D. Okay, so in D, this is where there's a typo. When element X reacts with water, it produces XOH and H2. The original one said Y. This is really exciting stuff, you guys, because what we're doing here is actual chemistry. We're decoding those unknown compounds using things like photoelectron spectroscopy, electron configuration, things that we as chemists do to decode elements we can't see, and then we put these symbols or these models on top of them. So X reacts with water to produce XOH, X being Na, and H2 gas. When we balance this out, I think we have to put a 2 here, 2 here, 2 here. So 2 NAs, 2 NAs, 4 H's, 2, 2, 4 H's, 2 O's, 2 O's. There we are, okay? Now we're gonna do some stoichiometry with this. So let's move on to problem 2. This was problem 1, and I'm gonna rewrite that reaction when I balance it here in a moment. Seriously? Come on, Rams. Okay. All right, so 2. We have the reaction 2Na plus 2H2O goes to 2NaOH plus H2. And we're gonna go ahead and do an ice table, ICE. 10 grams of X and 10 grams of water. Well, we gotta convert both of those to moles. So 10 divided by 23 gives me 0.434. I'm just gonna say 0.43 moles, and 10 divided by 18 is gonna give me 0.56 moles, 0, 0. I'm gonna go minus 2x, I'm gonna go minus 2x, I'm gonna go plus 2x, I'm gonna go plus 2x. Which one of these are gonna run out of? Well, you need the same amount, and you don't have the same amount. You have less Na. So I'm gonna put a 0 there, and then I'm gonna solve for X. So in doing so, solving for X, I get 0.43 divided by 2 equals X being 0.215. Okay, so then I'm gonna go through here and I'm gonna solve for everything. So 0.215 times 2 equals 0.43. And this isn't 2x, that's just x, so this is 0.215 moles. And 0.56 minus 2x, well, we know that 2x is 0.43, so 0.56 minus 0.43 equals 0.13. Okay, so essentially, we know that we have this many moles of excess, and we have this many moles of both product, but the world doesn't speak moles, the world speaks grams. So, and it speaks liters. So what volume of hydrogen gas is produced? So here's your hydrogen gas in moles, and if we want to know what volume, we need to plug it into PV equals nRT. So we know that the moles is 0.215, 0.0821, and T, they said, sorry about the squishy here, is 25, so it's 298, divided by P is 0.95 atmospheres. So I'm gonna go 0.215 times 0.0821 times 298 equals that, divided by 0.95, and I get 5.5, and let's look at the problem. 2 significant figures, so 5.5 liters of hydrogen gas, and it's an ideal gas, which is why we used PervNerd for that problem. What mass of oxygen, or what mass of excess reactant remains? So there is the excess reactant. We know the excess reactant is water. So water is a polar molecule, so we cannot use PV equals nRT. I can actually just use a straight mole conversion here. So I have 18 grams per every 1 mole, X grams per every 0.13 moles, and I'm simply going to multiply 18 times 0.13. 18 times 0.13 equals 2.34. So 2.34, but I'm just going to say 2.3 grams of oxygen. I'm going to stop the video and start a new one when we get to, and by the way, that was 3 right there. Start a new one when we get to 4.